Hi, thank you for the organizers for inviting me. I'm very pleased to be here, especially to celebrate with Bala, who I've known since I was a grad student at Washington University when you were visiting Cliff Will, while I was still doing post-Newtonian theory and not numerical relativity. So it's good to see you. So I'm at Cornell University. I'm part of a larger collaboration known as the Simulating Extreme Spacetimes collaboration, which includes Cornell, Caltech, AI, Potsdam, Cal State Fullerton, Washington State University, and many other places as our students have gone on to get faculty jobs. So what I'm going to talk about today is gravitational source modeling using numerical relativity. I'm going to give the overview of numerical relativity in what I've been told now is 20 minutes. So I'll quickly go through how you do binary black hole simulations, because those are what I'm more familiar with, and then also introduce what the complications are when you start doing binaries with neutrons, 1 or 2 neutron stars in them. And then Prayush Kumar is going to follow with challenges in future directions in BBH simulations, while Nathan will follow with challenges in future directions for the simulations with neutron stars. So why do we need numerical relativity? Well, the inspiral, as we've seen, can be well modeled using post-Newtonian methods when the velocity is much smaller than the speed of light. Numerical relativity needs to take over when VOC is large, and to go through the merger and the ring down. The ring down can also be studied using black hole perturbation theory, where you just perturb a stationary black hole solution. So numerical relativity needs to simulate the late inspiral and merger, and more importantly, it needs to actually determine what late means, that is where the post-Newtonian approximation breaks down, because numerical simulations take weeks to months to perform as opposed to using analytic waveforms. And so we need to use numerical relativity wisely to inform gravitational wave models that are built on top of the post-Newtonian approximation. So what do you do in order to solve vacuum Einstein equations on a computer? Well, you want to determine the space-time metric describing the inspiral, merger, and ring down of a binary black hole system. So this is done by solving an initial boundary value problem where you slice space-time into spatial hypersurfaces. You specify some initial conditions at some time, which has to be, in order to do a numerical simulation on a reasonable time scale, needs to be on the order of tens to hundreds, to at most hundreds of orbits before merger. On this initial slice, you need to solve what are known as the constraint equations. That is, Einstein's equations have constraints just like electromagnetic, the divergence equations of E and M. And then once you have the initial surface, you can use the evolution equations to determine the space-time metric at future times. Now, of course, this is all complicated because you have complete coordinate freedom in general relativity, and there are many, many bad choices of coordinates that you can make when doing numerical simulations that will cause your simulation to crash immediately. And it took years to find good coordinate conditions. And in addition, when you specify the initial conditions to describe a binary black hole system, the initial value formulation of Einstein's equations has you have to solve some elliptic equations, but you also have to specify some free data. But this data is not related to the masses and spins directly, so you have to use sort of an iterative type method where you guess what the initial conditions of a binary are, evolve them for a short amount of time to see if your binary is eccentric or circular, because we believe it should be circularized in most cases that we're going to be looking at. And so you have to solve this problem sort of iteratively. Then you have even more complications. You have to choose the computational domain in which to do the evolution. You have to avoid the physical singularities at the center of the black hole, so you have to make some choices there. You can either excise the inside the horizons of the black hole, or you can use what are known as puncture methods to deal with the singularities. You also cannot simulate the entire space-time to null infinity. We have to have a finite-sized computational domain in order to solve the problem. So we have to introduce some artificial outer boundary, and that means you have to impose some boundary conditions there that corresponding to no incoming radiation, and you don't want to have constraint violations flowing into your domain. Then you need to choose a robust numerical algorithm in order to solve the equations. You need to choose these coordinate conditions, which are very challenging to come up with. And even though mathematically the constraint equations of Einstein's equations are solved automatically when you evolve the system, numerically small errors small constraint violations can grow exponentially in time. So you have to have some way of dealing with these constraint violations. And so all this process took many, many years to come down. So if you want to choose a desired physical configuration with a given mass ratio and spins at some initial orbital parameters or an orbital frequency separation and radial inspiral velocity, as I said, you need to use an iterative initial data solve to get these desired parameters. You evolve for several orbits, measure your eccentricity, and adjust the knobs on your initial value conditions to reduce the eccentricity. Also, the physical parameters of the black holes will change slightly as you go from your initial slice to a slice, because there's an initial burst of what's called junk radiation that comes from the initial black holes because they're not in equilibrium when you specify your initial conditions. Once your desired setup is achieved, you then can evolve through merge and ring down until the waves reach your extraction surfaces, and then you need to extrapolate your gravitational radiation from finite radii, or either evolve it to infinity using some sort of Cauchy characteristic evolution. So the waveform extraction procedure typically works. You measure the radiation at several radii. Typically, we put our outer boundary between, say, 300 and several thousand times the mass of the system. At several radii you extract, and then you use the fact that, Newman-Penrose scalars have certain fall-off quantities as you go to infinity, and so you do a extrapolation in 1 over the radius and take out the leading order term. There are actually 3 different ways you can extract this waveform using either the Newman-Penrose scalars, what is known as the Reggie Wheeler-Zarrilli extraction method, or you can actually take data from your Cauchy evolution, put it on characteristic grid, which has null slices that go all the way to null infinity, and do the evolution on these null slices. And the good news so far is that for the level of accuracy needed for current gravitational wave detectors, all these methods of extraction agree with one another. The leading errors in the numerical simulations do not come from this waveform extraction. But as we go to future generation detectors, we'll have to revisit this issue and make sure that we know what we're doing. Also getting more of the details correct, such as the center of mass motion, and how you relate quantities that you measure in numerical simulations with those, say, in a post-Newtonian method, for example, definitions of mass and spin and tidal deformability. We need to get these details right as we go into the future. And a lot of these things are discussed in our recent waveform catalog paper. So post-Newtonian definitions, as we hear, come from a point particle prescription. The bodies are not treated as black holes. If you have spins, you also have spin supplementary conditions that you need to deal with. And the body multipole moments contribute to the spin effects. That is, a post-Newtonian quadrupole moment for a black hole is proportional to some power of the spin. And therefore, if you compare a binary black hole numerical simulation, you have to take into account those terms as well when you're matching to a numerical simulation. Numerical relativity definitions, the spin is defined by solving an eigenvalue problem on the apparent horizon of each black hole. The techniques so far have good accuracy for measuring the magnitudes of the spin, but there's still some ambiguity on actually the directions of the spins, and there are larger errors there. Finally, a quirk of the numerical relativity is that the mass of the black hole depends upon the spin of the black hole. And therefore, the mass is defined from the horizon area and the spin magnitude. Therefore, the mass is a secondary quantity in numerical relativity, whereas the mass monopole moment is you think of as a primary quantity in post-Newtonian. So getting the details right of this correspondence is going to be important in the future. The good news for numerical relativity is right now there are really several independent approaches and multiple codes that all give the same answer. So there are a set of puncture codes, which were the first codes to be able to robustly simulate numerical relativity binary black hole waveforms. They're fairly straightforward to implement. There's some open source infrastructure. They're good for short inspirals, and there are many codes, but most share common infrastructure. And then there's the code that was written by our large collaboration called the Spectral Einstein code, which uses a method which is more accurate and efficient and can do longer inspirals, 20 to 40 orbits in a reasonable time, where reasonable time is on weeks. And we've done a few simulations that have actually gone over 100 orbits. Our code is pretty much black box by now for mass ratios between 1 and 4 and dimensionless spins less than 0.8. That means we can run a large number of these simulations automatically. If we go outside this parameter range, we're successful. You may less and less as you push towards the extreme, but we're able to do simulations up to mass ratios of 10 to 1 with our code and spins up to maximal for nearly equal mass systems. The impressive thing about the puncture versus spec thing is that all these ingredients that I told you about that go into a numerical simulation, they're completely different choices are made in the two methods. Different initial conditions, different numerical algorithm, different formulation of Einstein's equation, treat the singularities different, do different mesh refinements, different coordinate conditions and different boundary conditions, and don't share a single line of code, yet their results agree to within the expected errors of the simulations, and these errors are currently much smaller than the measurement errors of LIGO and Virgo. However, once we go to future generation detectors, which will be able to measure the waveforms better, we will need to improve on the accuracy of these codes, and especially for the space-based detectors like LISA, where you can get signal-to-noise ratios of potentially 10,000 or so, our errors are not small enough numerically to do that yet. So, but we still have 15 years to improve ourselves. So what can be simulated now? The number of orbits before merger depends upon what question you're asking. If you're testing analytic models, you want to have some room where you believe the analytic model is accurate, so you want to do longer waveforms. If you want to look at the desired number of orbits for parameter estimation on LIGO data, then it depends on how long the signal was, of course. For signals that are longer than, say, 40 orbits, we'll need to hybridize a numerical waveform at the end with some sort of post-Newtonian-based waveform for the early inspiral. For the binary black hole problem, the total mass scales out of the problem, so it's an equal mass simulation that we do for a ground-based detector is equally applicable to supermassive black holes or LISA. Mass ratios between 1 and 20 have been simulated. There have been a few cracks at mass ratios higher, just as sort of a demonstration they can do, but this Q equals 100 case had less than 1 orbit before merger. So pushing to these higher mass ratios is a challenge still. Spins but less than 0.9 of maximal can be handled fairly routinely. Higher spins require improved initial data. Precession doesn't provide any additional challenges for numerical simulations nor eccentricity. Several groups have made available public waveform catalogs. It's an 8-dimensional parameter space, mass ratio, spin, and eccentricity. Our group has a catalog now that we've extended to over 2,000 waveforms, including 1,400 processing cases. The Rochester group has a waveform catalog with about 300 simulations, and Georgia Tech about 400 waveforms, most of them fairly short. And just to advertise our own waveform catalog, this shows sort of a coverage of the parameter space. You'll see that most of the simulations are for lower mass ratios between 1 to 4, where our code is more robust. We can just launch a large number of them. And they have a wide variety of number of cycles, including some that have over 200 gravitational wave cycles.
Is the accuracy good enough for a LISA?
So for LISA, not yet. Maybe for the comparable mass, low spin, we have enough accuracy with our code. But for third generation, I don't know. I haven't looked at it. I mean, we definitely have some room between current generation and the future generation where we have good accuracy. But I can't promise you we haven't done a detailed analysis of all our error sources, including the, say, extraction of gravitational waves for that generation detector. All right, so now I'm gonna move on to modeling binaries with neutron stars. This is an even more challenging problem than the vacuum space problem. So this is much more challenging. You should take all numerical simulations with matter in them with a large grain of salt. They might have the qualitative dynamics right in some cases, but the quantitative predictions, I would say, are still questionable. In order to describe matter, you need multi-physics. You need to describe general relativity, magnetohydrodynamics. Magnetic fields can be a very important post-merger, neutrino transport, because that carries away energy. You'll have electromagnetic radiation counterparts, which we'll hear a lot more about later in the week. And our process, nuclear reactions, are very important in these for predicting what the electromagnetic signals are. Furthermore, we're at such high densities that we don't know the nuclear equation of state, and that's one of the things we want to learn about by comparing numerical simulations and observations. In addition to the multiple time and length scales of the problem, you also have geometry changes. At some point, your neutron star will disrupt. You'll have black hole formation, and these present challenges when doing a numerical simulation where you have topology changes in your grid. So the binary neutron star case has a wide variety of outcomes depending on what the total mass of the system is. If the total mass is large enough, after merger, you have a very prompt collapse to a black hole. Depending upon the mass ratio, you may get a very minuscule disk or some disk, which could be capable of launching a gamma ray burst. If the masses are smaller, then you get, a either short-lived or long-lived massive neutron star. Here, this is the hypermassive neutron star case and a supermassive neutron star case. By various hydrodynamic and viscous processes, you get the formation of disks, and the hypermassive neutron star will collapse on a shorter time scale than over here. For the prompt collapse cases, these will happen when the mass is larger than some threshold mass, which we don't know yet because it depends upon the unknown equation of state, but it's probably at least 2.8 solar masses for the total mass. If you have prompt collapse, you'll end up with a final black hole whose spin is about 0.8. You'll have a negligible disk in the equal mass case, whereas if your mass ratio is larger than 1.25, you might get a percent or so of solar mass in the disk. In the massive neutron star formation category, your route you're going to take depends upon whether your mass is lower than the maximum mass that a spinning neutron star can support. If it's larger than that, then the lifetime of this object can vary between a tenth of a millisecond and 10 seconds, depending on which process leads to it to collapse. For the supermassive neutron stars, this could actually spin down due to magnetic field generation, and that may take on the order of hundreds or thousands of seconds. So looking at these different scenarios, we'll learn something about the equation of state when we compare it to gravitational wave observations. And gravitational waves from binary neutron stars, the post-merger waveform can depend a lot depending on the masses, spins of the objects, and the equations of state. And you see here for a variety of situations, very different features in the post-merger waveform. Finally, if we look at a binary system with one black hole and one neutron star, depending upon the mass ratio and the spin of the black hole, you'll get one of two cases where either the neutron star will just plunge into the black hole before it's disrupted, and you'll get an isolated black hole with no accretion disk, essentially. This will happen for large mass ratios, and for larger mass ratios, you can prevent it by having the aligned part of the spin of the black hole aligned with the orbital angular momentum, that will push you into the tidal disruption phase of the diagram, where you can get a black hole plus a disk. And if, for example, you can get a very large disk in some cases, if you had, say, a black hole that was near maximal aligned with orbital angular momentum, you can actually get a disk which may have up to half a solar mass of material in the disk. As in the binary black hole case, there are some public waveform catalogs by various groups. And in addition to producing the gravitational waveforms, the effects of the spin and masses of the holes and the equation of state have a big effect on the ejecta and electromagnetic counterparts that you'll see from these objects, where you can get short gamma ray bursts, R-process nucleosynthesis, kilonova, and synchrotron emission from these sources. So gravitational waveforms from numerical simulations of compact binaries are invaluable tools for data analysis and waveform modelers because you can use them to directly compare with observations. You can inform and test analytic waveform models, and you can construct what are called surrogate models, which are sort of approximations to fill in the parameter region where you can't do numerical simulations because they're so expensive. So it's like an interpolant between numerical simulations. And in addition, numerical simulations of these compact binaries will give you the properties of the remnants. They'll explore highly dynamical spacetimes, and they're also very useful to produce movies for public outreach. Thank you.
In the binary neutron star case, the picture that you showed, there was no scenario for producing a long-lived neutron star.
So,
in principle, you could have very light.
This case on the right is supposed to be a long-lived.
And it's again finally collapsing.
It's going to collapse on, if there's large magnetic fields that cause it to spin down, then the lifetime's expected to be on the order of thousands of seconds. Potentially, I mean, if there is not a large magnetic field generated, then it could last.
Because what I'm thinking is if you have light neutron stars, 1.2, 1.2, they could collapse, a lot of ejecta in that case because they're big neutron stars. You could have a very massive long-lived neutron star in that case. And that is possible. But are you saying that you still need large magnetic fields, small magnetic fields to stay?
So
in principle, you could have a 2.4 solar mass neutron star. We don't know whether they exist or not. So that's the case I was making.
Right.
But the simulations don't see it?
Yes. Well, so for the supermassive neutron stars, you can support for a rigidly rotating, fast-spinning neutron star. You can get up to 0.4 solar masses heavier than the corresponding maximum mass of a non-spinning hole. And so if that rigid rotation is what's supporting the object, then you need to have no magnetic field, otherwise that can cause the spin to go down and you'll cross the threshold. But of course, if you're less than the maximum mass of a non-spinning neutron star, if you have light enough neutron stars, then you could potentially have the long-lived neutron star.
Yeah. Do we expect a electromagnetic burst during the tidal disruption of neutron star?
There are scenarios that have been proposed for various things that could be precursors to the merger for these things, but I would say they're not agreed upon by experts in the field. So,
because in one scenario of the magnetar outburst, the tidal crack, the crystal cracks, I believe to be the
right. So there are no numerical simulations right now that have crusts.
Yeah. Okay.
So that's something for the future to explore.
Okay.
So hi. Sorry. So if you can comment on or expand on the comment that you made regarding waveform extraction. So if you want better precision, what we need to do, and will there be any preferred waveform extraction? Do we need CCM? Will CCM be the
Right, so-
one. Sorry. The other question is regarding neutron stars. If you're adding in the equation of state a strange component, do you see a difference in the numerical in the waveform, and will there be a way to distinguish between neutron star and strange star?
Okay, so the first question on waveform extraction. So we are exploring better techniques for doing Cauchy characteristic extraction, and eventually we'd like to do Cauchy characteristic matching. So the difference between the extraction and the matching techniques is the extraction, you just use the quantities you've extracted from your Cauchy simulation as the initial inner boundary of your characteristic evolution outward. In the matching case, you have feedback going both ways between the Cauchy code and the characteristic code, because that should more accurately model backscatter of radiation. And so that's something we're exploring. We've also, within our collaboration, so there's a characteristic code that had previously been built by the Pittsburgh group. It's known as the Pitt null code, which used finite difference methods. We've re-implemented that with spectral methods in our code, and it's much more accurate and much faster. And so we're hoping to use that on a lot of our simulations and to look at how accurately we can do the extraction. For the neutron star case, the question was differences in equation of state between, will that have an impact on the waveform? That's still no. So our group is doing some experiments where we try to get the same tidal deformability, but with two different equations of state, and see if there's any other signatures that would distinguish the two waveforms besides the tidal deformability, but that work is still in progress. I don't really have a result.
Okay, more questions we can have during the panel discussion. All the speakers you can ask, you can have more answers. So thank you for the